All right, so in our last example that we just finished up, we saw that this function, capital F of x, y, z, which was 2xy plus x squared, comma x squared plus z squared, comma 2yz, was conservative, which means it has a potential function. So let's try and find that potential function. We're going to use a mildly different technique than what we did last time for two variables, but the flavor of it is the same. And if you want to, you could use this technique with two variables as well. So if we think about that this is that little function f, and we're trying to find f, it would really be finding f such that this needs to be its gradient, which means that the derivative with respect to x needs to be 2xy. The derivative with respect to y needs to be x squared plus z squared. And the derivative with respect to z needs to be 2yz. It needs to be those corresponding components of f. So let's go ahead then and actually work with each of these to work backwards by integrating. So let's look to find f from each of them. So with this one, we're going to get that f is the integral of f sub x working dx. With this one, we'll work backwards that f should be the integral of f sub y dy. And with this one, we're going to do the integral of f sub z dz. So let's look at what each of those is. So the integral of f sub x dx is the integral of 2xy dx, which in this case, so the x is going to go up to x squared and divide by 2, so the 2's cancel. So we end up with x squared y. And then again, we get plus some sort of constant function, but this time there's more than one variable that's constant. When we're integrating with respect to x, both y and z are constant. So this is some function of y comma z. All right, let's do this one, f sub y dy. So this is going to be the integral of x squared plus z squared dy, both of which are constant, so they're both just going to gain a y. So we're going to get x squared y plus z squared y plus, let's give subscripts to these, so we really have like constant 1 function of xy, or sorry, yz. This one now is a constant 2 function. We did it with respect to y, so this constant will be x and z, because anything that has only x's and z's in it is going to have a derivative of 0 with respect to y. And then when we integrate f sub z dz, we're doing the integral of 2yz dz, which is going to be yz squared plus a third constant function, which this time is going to be with respect to x and y. All of these, though, should be the same function. They should all be f, right? F should be each of these. So now let's set them all equal. So I have the x squared y plus the c1 of yz should be the same as x squared y plus z squared y plus c2 of xz. And those should also be equal to yz squared plus c3 of xy. And what we're going to do at this point is just compare each of these to figure out what each of those constant functions need to be. So all three of these equations need to be equal to one another. So let's take a look at, for instance, c1 of yz. And we need to look for what's missing from this first equation that shows up in these second equations. So if we take a look at what we've got, well, x squared y, so notice though, we can only take things that are in terms of y and z. I'm not going to take anything that's in terms of x's. So notice I already have an x squared y in the first equation, so I don't need that, but I don't have this z squared y. And then I'm not going to take c2 of xz because c1 is only in terms of yz. So this should strictly be a function with z's and y's in it. However, there's a piece of c2 that I could take, which is also a piece of c1, which is a scalar. So don't forget scalars in this. They won't necessarily show up because they're inherent inside of each of these scaled functions, but there is some constant scalar c in there. What about c2? Well, and actually let's check this with the third equation as well. In the third equation, that makes sense as well, that we're missing that yz squared. So we're showing up here as z squared y. c2 of xz, well, for c2 with the first one, it's not missing anything. It's already got this x squared y term in there. And it's also not missing anything in the second one. Notice there's the z2y or z squared y is the same as this guy. Now notice this one has an extra piece that's not down here, but that's likely just a part of this because it's in terms of x's and y's. So c2 of xz is probably strictly just a constant. And then c3 of xy, well, this yz squared plus c3 does not have this x squared y. And then the yz squared probably just fits in this c1. And then same here, it's got the yz squared, but it doesn't have the x squared y. And then there's still a plus a constant showing up somewhere in there. So the goal is, if we found these right, if we plug all of them back in, we should have the exact same functions reading off then. So from all of these, we would then be able to see f of xy. Well, in the first one, when I plug this in, we'll see x squared y plus z squared y plus constant c. Right, we plugged in c1 and that's what we got. Let's double check. If I plug in c2, I again get x squared y plus z squared y plus c, which is good. And if I plug in c3, I get yz squared, which is here, plus x squared y plus c. So all of them then give the same function. So with this one, what we're doing is a little bit more of, let's find all three antiderivatives and then just compare them to figure out what the missing pieces are that are coming from each of them. So it's kind of like a puzzle where if I look at it from all three directions, then eventually I can figure out the function that it came from. And a good important thing is don't forget this plus a constant c. You just kind of have to add that in yourself because it's really a part of each of these. All of these has a plus a constant, a scalar constant. So if you want to use this technique with two variables, you can as well. You can look at f sub x and f sub y and figure out what's missing from the opposite ones to then put f all the way together. And again, if you want to check it, a good way to check it then is to just find the gradient of this, and you should get this function, as long as you did it right.